I was working with Sebastian on recently on flexural waves. So these waves, they obey instead of the Laplacian in the equation you showed, so it obeys like Laplacian square. And my question is is your methods applicable to this field, and what would be different, for example? What do you think would be?
We never looked at this B Laplacian, but so what I would try. You are dealing with this Subwavelength structure for B Laplacian, right?
Yes.
Okay, so I would try to get the analog of this capacitance matrix. There should be an analog. When you want to compute the resonance frequencies corresponding to that B Laplacian, there should be a finite dimensional matrix which give you the same thing, right? So it's much better to reduce the complexity of the problem. So don't work with somehow. I would not work with the PDE. I will try to approximate the PDE because I guess they are small parameters there. They are high contrast and so on. Otherwise, there is no subwavelength resonance. There is no reason for that. Okay, so because it's high contrast, you have that high parameter, that small or high parameter. It depends on how you look at it, and then try to approximate the PDE with a finite dimension matrix. When you compute the eigenvalues and eigenvectors of the finite dimension matrix, you are done, and you understand the structure much better in the finite dimensional space than in the infinite dimensional space.
Okay.
That sounds good.
Thank you.
So I would try this. I never thought about it, but I would try this.
And the dimension will be like the double, because here we have like 4 boundary conditions instead of 2.
Yeah, but then you include here the boundary condition, the transmission condition are. I don't think that this is a problem, right? So for the corresponding problem here, we can reduce it to finite dimensional thing. Okay, this is similar to what people are doing in quantum mechanics. That tie bending model is just.
Okay, thank you.
But then, because it's if there are waves there, because this is classical problem, so I would expect that the non-diagonal term, they don't decay fast. Okay? So you have to keep them. So here, as I said, approximating this with a capacitance matrix is fine, but that capacitance matrix, the off-diagonal terms are not zero. They don't decay fast. So it needs some work. Right? So yeah. So this capacitance matrix is for the Hermitian case, but we did it also for the non-Hermitian case with gain and loss, and we did it also for the time modulation thing. There is an analog of this. Instead of computing the eigenvalues, we compute a solution to some differential equations.
Okay, so do we have any more questions from the audience? I particularly encourage young researchers to ask questions to Habib. It's a wonderful opportunity to ask your questions directly to world leader in this domain. I mean, you can be a physicist or an applied mathematician, it doesn't mind. Any question is welcome. Okay, I've got one question. So towards the end of your talk, you were mentioning this time modulated media. Yeah. So you're saying that you are working on it. So can you say a bit more about that?
So basically, we introduced it exactly the same concept. We reduced everything to of course, to some capacitance matrix, and you can compute the eigenmodes. So in the time harmonic regime, you compute the eigenmodes just by solving the eigenvalue problem for that matrix. In the time modulated things, you solve a system of differential equations.
But for the time modulated thing, you need to make some kind of specific change of, variable, because in fact, you need to bring back your time modulated medium to some kind of, varying, moving frame. How do you do this? What's the algorithm?
I will send you the preprint.
Okay.
You will like it. It's very natural thing to do.
Okay.
So Eric is completing this, and it's very natural. I'm very happy about it.
Okay, so you think, because when you have this time varying media, for instance, your band diagram is tilted. Now you have this. I mean, everything is totally different, so you don't have any particular difficulty to analyze the spectrum. I mean, it's.
Yeah. So just wait. I will send it to you.
Okay.
And then a couple of days or a few weeks.
And I think I did not really understand what you were showing before with your topological states. You were showing some kind of spectral pollution around because you have a cloud of points,
This one?
Yes.
Okay, so it's described where it's described first here. Okay. Yeah. So you take your finite chain, right? Compute the eigenvalues. You will get them here, right? 1, 2, 3, 4, 5. Okay.
Yeah.
Now perturb the position of the resonators a little bit. Okay.
Okay.
So with this, you perturb the position and recompute the eigenvalues. And see how stable are these eigenvalues. When you increase the noise, when you increase then if it's not topologically protected, it's lost inside the bulk eigenvalues because it's in the top. And when it's topologically protected, it's exactly inside the band gap. So it's very far from this one and from this one. So even polluted with this geometric perturbations, it's still there. You can see it, right?
But usually they say also that it's topologically protected if the eigenmode remains localized, because here is the eigenvalue, isn't it?
Yeah, even the eigenvalues has to be inside the band gap.
Yes, I agree.
Assume that the eigenvalues is somewhere here. You perturb it exactly. This is what happened for all of this structure, right? So when I showed here, this one here. So this is defect mode, okay? But the defect mode is very close to this band, right? To this propagating band here. So any perturbation will bring you this guy inside. So it will not the mode will not be localized. So you may think about it also in terms of distance from the edge of this interval to this eigenmode, right?
Okay, and you were a little bit fast towards the end of your talk. Can we go back, to these plasmonics properties of this? Yes, this one, for instance. So, can we go through it a little bit more in detail? So, essentially, obviously, you're using some kind of conformal mapping approach, or to analyze this. No.
What we did. Okay, so there are two problems here. So we want to. What you want to do? We want to. You have two plasmonic resonators, right? You bring them next to each other, and then you want to estimate the blow up of the electric field, right?
Okay.
And we have estimate of the blow up of the electric field. It's here, right? It's analytic. This is kind of easy. So there is a blow up of the electric field in the gap, and we have estimates for it. Now, if you have many of these resonators, many of these plasmonic particles, a large system, and they are interacting, they are close to each other. You want to compute the field, or you're going to compute the hybridized resonance, right? So how you do it? So what Sanin introduced is this. Is numerical method for a system of close to touching plasmonic particles. How it goes? So you think about method of image charges, right? That expansion here, it does not converge for spherical plasmonic resonator, right? At the resonant frequencies, it does not converge. Why? Because this coefficient here is basically, it behaves like 1. It's 2 to power k. 2 should be the contrast or something like that. And here, 2 is here, is the contrast of this permittivities. And this guy at plasmonic, near the plasmonic resonance, it's almost 1. So you don't have convergence of this method of image charges. If you look at this transformation optics basis, it looks nice, but this coefficient of this transformation optics basis, they are not fully analytic, right? So what Sun Yun did is to convert the image charge solution into a transformation optics solution. This is the transformation. At the end of the day, you get an explicit formula where the coefficients are explicit and the series here is converging. Okay? Just converting the image charge method into this transformation optics, and you get this guy here. And the method, numerically speaking, is terrific when you compare it to other methods, because basically when you have the convergent series and everything is explicit, and you are sounds good. When you want to compute, this is when you want to compute the field, right? So you convert this because none of them is appropriate. One is explicit but not converging, and the coefficients are not explicit. Okay. When you want to compute the resonance frequencies, how you do it? So you compute the resonance frequencies of the pair here and the pair here. We have explicit formula for that. Where is this formula? There is an approximate resonance condition. We have a formula for it. You can compute those resonance, and you can compute those modes. And then you hybridize this, we call them transformation optics modes, this one and this one. You hybridize them by solving this couplet mode equation. It's very easy to solve. So you get the hybridized eigenmodes, which is the sum and the difference between the two here. The modes corresponding to the diagonal terms, and then the approximated resonant frequencies, these ones plus minus the interaction between the delta n is the interaction between, or the coupling between these two transformation optics modes. Okay, and that's all. And then you compare this numerically with respect to, of course, we don't have a theorem for this, but numerically it works pretty well. I answered your questions. So this is basically if you have a large system of close to touching plasmonic particles, and you want to compute the field, and you want to compute the hybridized
John Pendry also is, but it's slightly different. Is using this kind of mapping to help him analyze very finely this kind of close to touching.
Yes.
Yeah.
Yes. Yeah. So in dimension 2, you can do it by conformal mapping, right?
Yeah.
But
effectively, you are in 3 dimension. Yeah.
In dimension 3, you do it by this transformation.
It's it's very, really nice. Okay, so please come forward with your questions, guys and girls. I can see many people here, but it would be really, it would not be nice to name people, but it's a great opportunity to debate also. So even if you want to bring some controversial subject, please do. We want this to be a lively session. Just not 3 people talking.
Thanks, Sebastian. We will have many chances to debate about this. So
yes.
Hopefully we will go back to normal soon.
Let's give them a couple of minutes to react. Obviously, it was crystal clear, but please, if you want to improve your knowledge of topological properties or plasmonic properties, there's an opportunity here, rather than, taking paracetamol and trying to read a paper of Habib.
Yeah, we have a
easy
review
now.
paper. Yeah, by the way, Sebastian, we have a review paper where I think that Breen and Derek did a great job to make it as simple as possible. So the review paper is on my web page. It's the last one, the newest one, and it was for summer school I did in Italy. So that review paper is you don't need anything.
Oh, and actually it gives me the opportunity to mention that Habib is organizing with Agnès Morel a metamaterials school in Italy. This is, if I'm not mistaken, in July 2021. It will be mid-July. And it's another opportunity, you know, to learn more from Habib. So it will be in Trento, which is a lovely city, and it's mid-July. If COVID let us go there, anyway. Okay.
I have another question, Sebastian.
Yes, please do.
My question is, like, what is the reason for this hexagonal lattice to lead to this Dirac cones? And is it the only lattice that leads to the Dirac cone and these topological states?
Dirac cone, you need this symmetry. You need this honeycomb symmetry. Okay, so it's a geometric properties. So if you don't have, so you need the two curves in the subwavelength region. And you need them to you are asking about this one here.
Yes.
This comes from the symmetry from this honeycomb symmetry. So they will cross each other. Then you have to prove that this is the canonical behavior. So you have to prove this things here around the crossing point, right? But the fact that they cross each other at this K point is because of the symmetry. The fact that this is canonical behavior, I don't think that it follows from the symmetry. You have to work a little bit. And as you can see, the first mode is a monopole, and the second mode is dipole, and then they cross each other, and then you get the dipole, and then they are stopped.
Okay.
I have a question. I don't know if you hear me.
Yes, great.
Hello, it's Kim. I have a question. Have you applied this theory to other kind of subwavelength resonators, such as Helmholtz resonators, where you have a contrast only in geometric parameters?
Yeah. So for actually for Helmholtz resonators, that was our starting point. But it was so what we did for Helmholtz resonators, we did this where. Here. I'm sorry. Here, this one here. So this paper in communication math physics, that was starting point, and there we started with this Helmholtz resonators. Coupled Helmholtz resonators prove that they have subwavelength resonance, and around that subwavelength resonance, we can achieve subwavelength. We can achieve super resolution. So I think that the experimental work was done by Matthias and his group, and in this paper we made the math framework. So we proved that the imaginary part of the green function of the subwavelength resonators, Helmholtz resonators, the imaginary part has a peak. Okay. So this is 2015 paper. Then, if proving all of these results, it's much better to do it in the simplest model, at least for us, because we want to prove theorems and so on, and derive some formula and asymptotics. So in principle, it could be done, and I think in principle it should be painful if you want to extend it to this Helmholtz resonator, but should be there. I'm sure it can be done. Could be interesting, I'm sure, but could be painful. So this is the only thing we consider. So if you look at this paper, it's 15 pages or something. Hai did a fantastic job. So, then extending this theory, because we are coming from this layer potential techniques and so on, integral equation. So extending that theory to Helmholtz equation and proving this band gap opening and so on, it's feasible, but it's painful.
Okay.
For plasmonic reasons, for plasmonic particles, we did part of it. For plasmonic particles,
Okay, thank you, Habib.
Thank you, thank you.
So, do we have any more questions? Even from people, you know, who might be in a remote field or, you know, of seismic waves, or, you know, there might be some similar phenomena. I think that what Habib is modeling goes way beyond just electromagnetics and acoustics. This theory can be applied, I guess, to elasticity, full elasticity.
Could be.
I mean, what would be the main difference? I mean, obviously, then it becomes vectorial, but in elasticity, you have the Helmholtz decomposition theorem.
Yeah.
You can, yeah.
So there is Sebastian. So just to mention, there is a technical point even for Maxwell's equation without going to for Maxwell's equation and for elasticity. So here everything is based on this, at least from our work, and based on the layer potential techniques. And for the corresponding operators for elasticity or the corresponding operators for Maxwell's equations, they don't have this compactness properties. So at least one of them, this volume integral operator, it even has zero as essential singularity. So some work is needed. So we did it for Maxwell's equation, but we never did it for elasticity. Should be possible for elasticity, but for Maxwell's equation we did it. One of these recent papers on super resolution for Maxwell's equations, and it's hard to deal with these non-compact operators or with operators with non-compact in elasticity. In Maxwell's equations, they are still compact, but they have zero as essential singularity, and then.
So there is a big jump in terms of.
There is some jump, not big, but it's technical. It's a just technical jump.
But I guess perhaps if you have, for instance, fibers, because in fibers, you know, you have this case whereby you can still model, for instance, propagational light in microstructured fibers with some kind of coupled Helmholtz equations. So you have two Helmholtz equations, one for E and one for H, which are coupled through the boundary conditions.
Yeah, that should be okay. They are scalar equations, that should be okay.
I have but one case that would be kind of similar is the case perhaps of water waves, you know, because again, it's Helmholtz equation, but it's set on the free surface, you know, of the liquid.
Yeah. That should be okay. Yeah, that should be.
So you just need, okay, but again, going back to the question which was asked by Mohamed Farhat, you would not be too scared by going to a bi-Laplacian. You would keep all the good compactness properties or whatever of your operators.
Yeah, the bi-Laplacian should be okay. Even Maxwell should be okay. Even elasticity, I'm sure that we know how to handle. But from technical point of view, it's something has to be done. It's not completed.
Can imagine. Okay, so do we have any more questions? Especially, I like to have questions from, you know, PhD, postgraduates, postdocs, because these are the people who can beneficiate most from interactions with a senior leading researcher. I know that there are some people, for instance, in Femto right now Julio? No. Nicolas? I'm naming people now, I'm bad. Yeah. Okay, so if we don't have any more questions, it's your last chance. Then I would like to thank again our speaker for this fantastic talk. It was a great survey of the field. And so I hope to see you back very soon. So next time we will have the pleasure to welcome Vincent Pagneux, who will give a talk on also some kind of spectral problems. And let us, well, thank again our speaker. It was really, really nice to have you with us, Professor Ammari.
Thank you very much. Thank you. Thank you. Thank you.
Thank you.
Thank you. I appreciate it. Thank you so much. So keep all safe. And hopefully see each other in person soon, right?
Yeah, it would be great. If we can meet in Trento, it would be fantastic. So
yeah.
Everyone, you know, summer school, Trento, mid-July 2021.
Yeah.
That's a great, great venue. Great, great summer school. Okay, bye-bye. Bye-bye, everyone.
Bye. Bye. Thank you, Sebastian.